We can start now.
Welcome everyone to today's seminar. It's a pleasure to introduce Mark Hollands from the University of Warkwick in the United Kingdom. Mark completed his PhD at the University of Warwick, working with Boris Genschike, data mining metal-rich white dwarfs from the Sloan Digital Sky Survey. He's now working with Pierre-Emmanuel Tremblay, also at Warwick, on white dwarfs in the ESA Gaia survey. Thank you so much, Mark, for accepting our invitation. And you may start when you are ready.
Okay, yeah, thank you for inviting me, first of all. So hopefully you can see my slides again on the screen. Can I just double check, can you see the mouse cursor as well? Okay, that's great. So I can point at things, perfect. Yeah, so I'm going to make this a talk of two halves, basically, because I know some people in the audience will not be familiar with the topic of white dwarfs or the white dwarf planetary systems. So I will be starting with a nice, easy introduction to white dwarfs and the exciting results, especially from the last few years for their planetary systems. And so those in the audience that are familiar with those topics, you should find this a nice relaxing part to the talk, but then we'll get on to some of our new results that we had published in Nature Astronomy last month. And so hopefully you'll be able to find that interesting too. So yeah, I'll get on with the main talk. And so any good white dwarf talk will always start with a Hertzsprung-Russell diagram. And so this is one that I decided to show you today. And we have the GBP minus RP axis, which essentially corresponds to temperature. So hotter objects to the left and cooler objects to the right. And then the y-axis is the absolute G magnitude, so brighter objects to the top and fainter to the bottom. And we have essentially two sequences that you see in the figure. The main sequence, where we find stars like the sun, and you can see some things starting to depart from the main sequence and ascend onto the giant branches. But down here we have the white dwarfs, which are very clearly separated in the Gaia HR diagram. And the reason I like to talk about HR diagrams even when I want to talk about exoplanets is when normally we hear the phrase exoplanets, we think of stars over here on the main sequence, and we think of transits and radial velocities. And of course, there's many exciting results that come out of studying these systems. But the planetary systems don't disappear after the stars leave the main sequence. Certainly some planets might find themselves engulfed during the giant branch. But many planets will also survive the giant phases, and in fact they'll move on to wider orbits due to mass loss. And as the stars move across and come down onto the white dwarf sequence, we should expect a large fraction of a planetary system to survive, and therefore for there to be planetary systems orbiting white dwarfs as well. And so therefore we can look at white dwarfs in different kinds of ways to learn about planetary systems beyond the main sequence, and essentially use white dwarfs as a separate tool to learn things that we can't do with the main sequence alone. And so before we move on to learn about those planetary systems themselves, it's worth bearing in mind a few different things about white dwarfs themselves. So I'll just move something. So a typical white dwarf is a very compact object, slightly bigger than the Earth, and with an average mass of about 0.6 solar masses. And so compacted into about 1% of a solar radius, we're talking about something that is very, very dense. And I should say that this mass is just the average mass. You can get some slightly lower and some that are higher. But just a typical white dwarf will have a surface gravity log G of 8. So that's 1,000,000 times the acceleration that you experience just sitting on your chair watching this talk. So we're talking extremely high surface gravities, and that has a strong effect on the white dwarf structure. So a very basic schematic of a simple white dwarf, a typical white dwarf, has a carbon-oxygen electron degenerate core where almost all, 99% of the mass resides. And that's enveloped by a layer of helium, which makes up about 1% of the mass. And only the very outer fraction of a percent of the mass actually is hydrogen. But when we point a telescope at a white dwarf like this, that is exactly what we see. We see the very outer layer only of the hydrogen. And so we would expect, because of the high gravitational field, sorting the elements in order of their weight, that we would see a very clean spectrum with not much else except for hydrogen. This hydrogen layer is not actually present in all white dwarfs. In about a quarter of white dwarf stars, you can have a very late thermal pulse at the end of the AGB, which can burn off the remaining hydrogen and leave you with mostly helium in the atmosphere of the white dwarf. And so when you point your telescope and take a spectrum of a white dwarf like this, you see a helium spectrum instead. And so you get lots of helium lines in your spectrum. But you don't expect to see elements heavier than helium, simply because of these high gravitational fields that I mentioned that sort of force the heavy elements out of the atmosphere and the lightest ones to the surface. And despite that expectation, we in fact see lots of white dwarfs with metals in their atmospheres. And so this is a spectrum of a star called Van Manen 2 or VMA2. And this is in fact one of the first, I think maybe the fourth white dwarf ever discovered. It was certainly the first white dwarf discovered that was not part of a binary system. And its spectrum has very strong features of calcium, magnesium, and iron in the spectrum. And as we will see, these spectral features relate to a planetary system. And so this was just first discovered in 1917. This is not the original spectrum. This is a nice new one from UVES. But the original spectrum, we can still see the calcium H and K lines quite clearly. And this star was initially classified as an F-type star, and it was only a few years later when a parallax was obtained that it was clear that it was a white dwarf star. But we now know that these two absorption features actually represent the first evidence of any kind of exoplanetary system at all. But the issue was that the interpretation did not come for almost a century later. But now we understand that this is a signature of a planetary system. But this mystery of how some white dwarfs can have metals in their atmosphere, that didn't start to actually be understood until almost the end of the 20th century in the late 1980s, observing a star called G29-38. So in this star, when you look at the optical photometry versus the infrared photometry, in the optical, we have the amount of flux that we would expect, but at infrared wavelengths, there is a lot more flux, a so-called infrared excess. And this was reported by Zuckerman and Becklin in 1987. And they suggested maybe this flux comes from a brown dwarf companion, but they suggested maybe also it could be dust in a disk orbiting close to the white dwarf. And it was later proved that it had to be dust due to pulsations of this white dwarf. And a few years after that, it was discovered this star also has metals in its atmosphere, like the one I showed before. And so the picture we now have in our minds is something that looks like this. So a white dwarf like G29-38 surrounded with a debris disk of dust within its Roche radius. And this dust can flow onto the white dwarf atmosphere and produce the metal lines in the spectrum. We also see a big gap here, which shows that some of the dust will be ionized close to the white dwarf and will actually flow onto the star as gas. This can also be detected as emission lines in some cases. But what I've described so far doesn't really solve the problem, it just moves the problem. We've said, oh, where do the metal lines come from? And we've said now they come from a disk, but the question is, where does the disk come from? And it wasn't until 2003 that an astronomer, Mike Jura, suggested that if white dwarfs have intact planetary systems, there will be lots of gravitational interactions between different objects, and say large planets would be able to scatter smaller objects potentially towards the white dwarf. And that includes asteroids and minor planets. And so the picture we have now is that the metals in the atmosphere and the debris disks that we see arise from incoming planetesimals that get disrupted by the tidal forces close to the white dwarf, and then form the other observational features. So with this in mind, knowing that the metals now come from planetesimals, we can use the white dwarf spectroscopy to learn about what exoplanets are actually made of. And so here what I'm showing is the ultraviolet spectrum of a white dwarf Galax 1931, published by Genziker et al. In 2012. And they find a lot of different elements in this star, in the UV especially, where you have lots of lines. So oxygen, magnesium, manganese, chromium, iron, nickel. So there's lots of elements that you can use and measure. And so what you need to do is you need a model atmosphere to be able to replicate all the features in the spectrum. And when you do that, that allows you to essentially measure how much of each element is in the stellar atmosphere, which is indicated by the red curve over the data. And so, for instance, if you were to detect a lot of iron and nickel in the spectrum and not so much else, you would have a clear case for material that looks like a planetary core. And indeed, in some white dwarfs, that's exactly what we see. In others, you would see maybe lots of magnesium and silicon, and that would be a strong indication of a planetary mantle type material. And so there have been lots of different white dwarfs that have been analyzed in this way, but I want to just show you a couple of highlight objects that I think are particularly interesting. The first of which is GD61. This is a white dwarf that has lots of metals in its atmosphere that correspond to rocky material, but it's also thought that the asteroid that it would have accreted would have contained lots of water ice as well. And the reason that Farihi et al., who published this, came to that conclusion is by looking at the amount of oxygen in the atmosphere. And they assumed that every metal comes from some kind of metal oxide, so iron oxide, magnesium oxide, etc. And after they did this, they still had extra oxygen left over, almost half. And so you need an extra molecule to put this oxygen in order to deliver it to the white dwarf. And the only real candidate is water. And this makes even more sense when you consider that GD61's atmosphere is mostly helium, but there is some trace hydrogen in there, and it's comparable to the amount that you might expect if the rest of the oxygen is from water. So that's a particularly nice discovery. But the things I've discussed so far are all talking about rocky things like asteroids and minor planets. But we also see evidence in at least one case of a comet-like object or a Kuiper belt-like object. So Zhu et al. In 2017, just a few years ago, looked at this white dwarf 1425 and the abundance patterns in the atmosphere enhanced in sulfur, nitrogen, and carbon. And these are not elements that are particularly prevalent in rocky material, like in the Earth. But if you look at the comet Halley, it's almost a perfect match to the abundances. So it really shows the power of what you can do with the spectroscopy in matching to different types of planetary objects. And things really, I guess, accelerated in the types of observations that we were getting, and sort of really completed the picture if you want, in 2015 with this discovery of WD 1145 plus 017. And this white dwarf, it kind of has it all, if you want. It has metals in the spectrum. It has the infrared excess that I said before is a signature of the debris disk around the white dwarf. But what it has extra is that Van der Berg looked at the Kepler data and got a nice light curve and saw that there are lots of transit features in the light curve. And so the light curve I show now is is a little bit newer than that one, taken in 2016. But what you see is there's lots of different transit features that come and go every 4.5 hours, and then after several orbits, maybe a couple of days worth, each feature will disappear and new features will reappear. And so what you're looking at is the actual breakup of debris itself, producing lots of dust, which can obscure up to half of the starlight from the white dwarf at a given time. And so, yeah, I think this really completes that picture of an asteroid coming in and breaking up and flowing onto the white dwarf atmosphere. But now we're starting to get to the point where we're actually seeing even more direct evidence for the planetesimals and even planets themselves. So a couple of years ago, a colleague of mine, Christopher Manser, who's now at Imperial College London, was looking at this star SDSS 1228 plus 1040, and he was looking at the emission features of calcium, which I mentioned indicate gas within the disk. And you see these double peaked features because as the gas flows around, it gets red shifted as it goes away from you, and as it comes back round, it gets blue shifted. And so when you see all the gas together, you get double peaks, which indicate a disk structure for the gas. And what Chris did was to take lots of spectra across a night to see if there was any short-term variability. And so this shows a sort of spectral trail over time or phase. And just looking at this, you can't really see that anything is happening. It just looks fairly constant over time. But if you subtract just the mean value at each wavelength, you're left with these very distinct stripes going diagonally across that occur every 2 hours. And 2 hours corresponds to an orbital period that should be within the disk. And so Manser et al. Gave an explanation that this comes from a planetesimal, perhaps say an iron nickel core that's unable to be broken down at the moment, but is orbiting within the disk and stirring up the dust and gas and essentially modulating the gas emission on a 2-hour timescale. But things have started to get even bigger. And so towards the end of 2019, Ganziker et al. Reported in Nature a white dwarf that actually appears to be accreting from a gas giant planet itself. And this is WGJ0914. And what they observed, it also has emission lines that are double peaked. But instead of being from rocky elements like calcium and iron, they're actually seeing oxygen, sulfur, and hydrogen instead, and no other elements. These are the only three. You also see oxygen and sulfur in the white dwarf atmosphere. You can't see the hydrogen because there's already hydrogen there, but trying to compare what kind of material can come that can be accreted that only has these three elements. The only thing we know of in the solar system, the ice giant planets like Uranus and Neptune, their sort of inner envelopes are made of water and hydrogen sulfide. And so the picture appears to be that the outer layers are being stripped off of a closely orbiting planet that is forming a gas disk of oxygen, hydrogen, and sulfur, and that's flowing onto the white dwarf atmosphere. So in a sense, this is the first detection of a full-size planet that we can fully say is completely a planet and not just an asteroid. But if you're an exoplanets person, perhaps you really need transits to convince you when a planet's a planet. And we now have observations of this kind of system as well, reported last year by Andrew Vanderberg, where that they discovered, looking at test data in WDJ 1856, which is a fairly nearby white dwarf, only 25 parsec away. They discovered very deep transits in the light curve. This is actually from the GTC and Spitzer, which are very high quality light curves, but you can see over 50% of the white dwarf flux gets blocked at the mid-transit. And so they've determined that this has to be a giant-sized planet orbiting close to the white dwarf on a 1.4 day period. So we're now actually seeing full-size planets themselves. And so just to finish off this section of the talk, I like to sort of construct this kind of thing into a pyramid of observation types. So in terms of transiting planets and accreting gas giant planets, we have one each of those. We have a couple of systems now where we see the breakup of planetary debris transiting the white dwarf, like white dwarf 1145. There are a bit more than 50 systems that have disks that you see in the infrared, and with maybe a bit less than half of those also having emission lines from metallic gas. But what we see a lot of in a lot of white dwarfs is just the metals in the atmosphere. And so I guess I'm going to be talking mostly about these systems for the rest of the talk. But the fact that we find so many white dwarfs like this, I think, is really important to keep in mind. Really gives us the power to study a lot of systems and see some particularly interesting outliers. I mean, a couple of them that I've already mentioned, but now we'll be seeing some new ones. And so that will take me actually back, first of all, to my title slide. And the reason I want to show this again is I've shown quite a few pieces of artwork of other people's discoveries. And in pretty much all the other cases, the star has been depicted as blue. And the reason for that is that the other systems have all been hot white dwarfs, so 10,000 to 20,000 Kelvin, maybe even up to 25,000. Whereas the systems we're looking at are much cooler and very old white dwarfs. And in fact, they can be much cooler than the sun. And so they will actually appear orange to your eyes. So that's why we chose to go for this color instead. And the type of white dwarf that I'll be now talking about is called a DZ white dwarf. And this simply means that the dominant spectral feature is from metal lines. And I've already shown one of these near the beginning of the talk, which was Van Manen's star. But usually these have helium-dominated atmospheres. So where below 12,000 Kelvin, there are no helium lines because helium becomes, well, it's almost all in its ground state and there's almost no transitions. But actually below 5,000 Kelvin, the same thing happens with hydrogen and you're only left with metal lines again. And so the thing to bear in mind is, yeah, like I said before, we're talking about low temperature stars. And this means old ages for the white dwarf. So at least 1 billion years. And actually the objects I'm talking about here are all in the range, going to be in the range 5 to 10 billion years. But the other important feature that DZ white dwarfs have that I need to mention is that they have deep convection zones in their outer envelopes. And a lot of the stars I've mentioned previously are a bit different. So the ones with disks that they are accreting from, you're looking at something that is in the, it's accreting material into its atmosphere, and then that material is diffusing out of the atmosphere, and you reach an equilibrium where where you have material flowing in and material flowing out, and you're capturing that at a constant rate. And that's really good because it means you can measure the actual accretion rate onto the white dwarf for each element. But on the other hand, it means that you can't really say much about the mass of the planetesimals. Whereas in these cooler white dwarfs, the convection zones keep the material suspended in the outer layers for a very long time. So if you sprinkle some metals into the atmosphere, the convection zone will potentially keep it there on timescales of millions of years, which is, we think, a bit bigger than the amount of time that disks last for. We think maybe disks last for 10 to the 5 or 10 to the 6 years just about. But we think that the diffusion timescales are about an order of magnitude larger than that. So 10 to the 6, 10 to the 7. So when you look at DZ white dwarfs, at least in most cases, we think that the disk has gone and the materials that you see in the atmosphere are sort of left over. But this at least has one different thing you can observe, and that's if you're able to calculate the size of the convection zone using your white dwarf models, and you measure how the fraction of elements in the atmosphere, you're able to actually measure how much metals have been accreted, and say something about at least a lower limit on the mass of the planetesimals. And that brings me, I guess, now to my actual work, that finally, where we discovered some cool white dwarfs with these alkali metals, lithium and potassium in their atmosphere. Also sodium, but we see that in a lot more objects anyway, because that's already a large component of planetary material. But the reason we were able to find these objects is we were building a sample of all white dwarfs within 40 parsecs of the sun, and actually we're still working on that. But the preliminary results for the Northern Hemisphere were published by Tremblay and McCleary et al. Last year. And in the process of doing this, obviously we inspected lots of different objects and their spectroscopy. But because Gaia means you find pretty much everything, at least for nearby white dwarfs, we were able to find these very, very cool white dwarfs that were previously very difficult to detect. And that means that we can see elements in their atmospheres that wouldn't have been easy to detect at higher temperatures. And as I say, this means that we're looking at very old ages. So now I'm going to sort of introduce you to our characters in our story, starting with LHS 2534. So this was the first one we found with lithium, but we weren't the first people to discover this star. It's been known actually about 20 years because it has this magnetic field, which causes Zeeman splitting. If you think back to your quantum mechanics, that causes each line to split into 3 components. And so we have a few different elements here: iron, calcium, chromium, sodium, which is a very strong feature in the star, lithium, you can see, is a small feature here, and potassium. And the reason these elements weren't discovered before is just because the spectra were not as high quality as they needed to be. But with X-Shooter, when we zoom in, we can see quite a clear Zeeman triplet of lithium for the 3 components. And for potassium, we also see, well, 6 components here for horrible quantum mechanics reasons, but this is exactly where you would expect the components to be at this field strength. Yeah, so we were able to get both lithium and potassium in this object. But moving to cooler temperatures, we found this object next, which WDJ2317, and we don't see as many elements in this star, but we do still see calcium, sodium, and lithium. And this star has a couple of other interesting properties. Its mass is quite large. It was clear just looking at the Hertzsprung-Russell diagram that it needed to be close to 1 solar mass. And it also has a mixed composition atmosphere. So the background elements are hydrogen and helium mixed together in about a 1-to-1 ratio. Similarly, we found next 1824 plus 1213, which has a slightly different looking spectrum, but it also has a mixed atmosphere. So hydrogen and helium are both about 1-to-1 ratio. And then the trace elements, which I should say, I guess, like they are trace. We're talking about 10 to the minus 10, or in lithium, it's 10 to the minus 11 of the atmosphere by number. But we see these same elements again, calcium, sodium, and lithium. And finally, we found actually a fourth object, not in our 40 parsec sample, excuse me, but just double checking the Sloan Digital Sky Survey and their spectra, we found one further object. And this object, again, had been known before, but the lithium line, I think no one had thought to look at this wavelength carefully before. And we were able to see that there is, in fact, a lithium line there, as well as calcium and a very big sodium feature. This is almost a pure helium atmosphere, at least for the background element. There's not really any hydrogen here, and that means that the lines are a lot broader. So that's why the spectrum looks quite different. And what we want to do next, now we've got our 4 white dwarfs that we found, is to actually compare them and see how they compare with different types of solar system bodies. But to do that, we actually need to model the spectra, and that turns out to be quite challenging. And the reason very much is because these stars are so cool. At 3,000, or at least below 4,000 Kelvin, we're really pushing the limits of what white dwarf model atmospheres can do. And the reasons for this is because how transparent the atmospheres are. There's not many sources of opacity beyond the metal absorption lines. And so the depth of the atmosphere where the photons actually escape from corresponds to extremely high density. So we're talking actually almost a plasma that is practically the same density as that of water, which is, for instance, that's about 10 to the 7 times higher than the density you find in the solar atmosphere. So it's really pushing the limits of our models. And you also need to account for molecules in the atmosphere. So at these temperatures, although you might not be able to see the hydrogen from lines, it's certainly there, and it can show itself from collision-induced absorption features, where you have, say, hydrogen molecules impacting other species, such as, well, most importantly, hydrogen molecules colliding with helium atoms, but also hydrogen atoms and other hydrogen molecules. And so this can produce other spectral features that I will mention in a bit. A couple of things that I will talk about in a minute, but one of the things we found quite challenging is that the masses that we find tend to be a bit on the small side. And this isn't something that is unique to the models we're using. Other people are looking at cool white dwarfs, not necessarily with metals, have also had similar difficulties in the past. But one thing we specifically did find very strange is the lithium lines themselves are very different in shape to how we would, or at least what our models predict what they should look like. And so that presents another challenge in the analysis. But when we compare our models with the data, at least in a superficial way, they actually look quite good. So in the top row, we have all of the spectra, and the red curves are the models for the optical spectra. And at least for, say, LHS2534, it looks fairly good overall. And the same for the other objects. And we can even, say, reproduce this very broad sodium line in this star, for instance. And then when we look at the photometry, so a larger dynamic range in flux that you can see here, we're also able to reproduce the photometric points fairly well in most cases. For this star, we had trouble fitting the infrared fluxes, but I will talk about those more separately in a bit. But you can see this broad absorption bump in this star, and this one especially, which are caused by these hydrogen molecules colliding with helium atoms. And so it seems that we can do a very good job of actually reproducing the shape of the spectral energy distributions. But when we actually look at the results that we get, in some cases they look a bit strange. So for this star, we find a mass that looks fairly reasonable, kind of what we expect for a normal white dwarf. For this one, it is very high mass, which is actually quite exciting because of a star of this mass, or a white dwarf of this mass, would have to have a progenitor star of a B type on the main sequence. And so we're looking at a planetary system from a B-type star, which isn't something that you easily see in normal exoplanet studies. But these two stars, which are much lower in effective temperature, the masses that we find, as I say, is a bit too small. And the reason is that within the age of the universe, you don't expect there to be any white dwarfs with masses much less than 0.45 solar masses. And yet we're coming out with numbers like this. So it certainly suggests that there needs to be improvements to our atmosphere models for dealing with these very low temperature stars. And so it's more likely that they have more reasonable masses and slightly higher temperatures instead. And I also mentioned that issues with modeling the lithium lines. Here, I will just talk about this particular panel first of all, but the data is in gray, and the orange curve shows the shape of the line profile that we would expect to see with the atomic data that's publicly available. And yeah, you expect to see a line core, but you should see very strong line wings as well. And there are basically no line wings in any of these objects. Right, it's just, you just see this narrow core shape. And so we played around with the atomic broadening constants until we found a good match for this particular star. And indeed, for the other object, with these two both have mixed hydrogen plus helium atmospheres, and so we also did an all right job at reproducing this line shape. But the two objects with mostly helium in the atmosphere, we were still not able to fully reproduce the line shape, although we were still able to fit the equivalent widths of the lines. And so that brings us, I guess, now though onto our abundance analysis and how we actually found that compares with different types of planetary objects. So what we have here are our 4 cluster of points for our 4 stars, looking at their calcium to sodium ratios and their lithium to sodium ratios. And we see they form a nice cluster up here in this parameter space. And these gray lines extending out of them represent the abundance as it changes over time, or looking back into the past, because it takes, say, 1 million years for calcium to diffuse out of the atmosphere, but say 4 million years for lithium to diffuse out the convection zone. And so over time, the actual observed abundance ratios will change. And so this represents if you accreted the original material several million years ago. And we can see, say, for this star 2 million years ago, we would have had something that looks like the continental crust of the Earth. But maybe more like 4 million years ago, it would look closer to chondrites. And maybe these objects could potentially have looked like the Earth in the past. And so the question is, what kind of objects can have produced, what kind of planetary objects could have produced this kind of abundance patterns? And we only really can explain that with LHS 2534, where we have a potassium detection as well. And we find, again, 2 million years ago, the composition in the atmosphere would have looked exactly like continental crust. And so and at no point in the past could it have looked like these other types of planetary object. And so our main conclusion is that at least this object has accreted a fragment of a planetary crust. And given that the close proximity to the other objects, we at least suggested that these could also have accreted planetary crusts. And so I'm quickly going to go back, though, to one of the objects that I want to talk about in a bit more detail, because this star is quite exciting. So I said before we couldn't fit the infrared photometry very well. Well, if we suggest that maybe there is an infrared excess, we were actually able to fit the photometry much better or simultaneously. But we were a little skeptical of doing this at first, given that we thought there are potentially issues with our atmospheric models, particularly that could be the result of these molecular features. But actually, when we compare just the photometry of this star, so ignoring models completely, with other similar white dwarfs of similar temperatures, so here we have the Gaia BP minus RP color. For a similar color of this, we find that there is a huge difference in the WISE color, and that's sort of a 4 sigma difference. Or in other words, it's a way of saying that this curve here, or these 2 points here, are very flat, where we would expect a steep slope instead. And so this is still a bit more indication that there could be a disk. But the sort of final thing that convinces us there must be a disk is actually analyzing the convection zone itself. And so I'm just going to show you this table very quickly, a big horrible table, but the size of the convection zone that we measure is actually in this object, because of its very high mass, that's about 1 solar mass. The convection zone is about 3 orders of magnitude smaller than for the other objects. And as a result, its diffusion timescales are much smaller. So instead of millions of years or even tens of millions of years, it's only a few thousand years for the elements to persist in the atmosphere. And so you almost require to have a disk to replenish these elements to make it at all likely that you would even observe these elements. And so we feel this makes it very clear that there has to be a disk. This also means you can measure the accretion rates of each element onto the star. And this shows actually how precise you can do. For lithium, to get the absorption line in the spectrum, we only actually need about 1 kilogram per second, or even less than that, for the whole star to be able to produce this lithium line. And assuming crust, this corresponds to about 3 tons per second over the whole star. And this is this object is much older than any other object known with a disk, with this one at 10 gig a year in its cooling age. And just to finish off the talk, I really need to talk about another paper and compare against, because while we got this work published in February, we were slightly beaten to the punch by Kaiser et al., who they got their results published in December, where they found a star J1644 that also has lithium and potassium in its atmosphere. They also rediscovered the lithium in SDSS J1330, but they had a different explanation for lithium, where they suggested that because these white dwarfs were, or at least this white dwarf was formed so many billions of years ago at the very start of, early in the Milky Way's history, there would have been a lot more lithium available. And so the earliest planets formed in the Milky Way would have had more lithium for that reason. And so the question is there actually room for both explanations? Is one of us wrong, or are we both right, but for different systems? And so just to quickly show the spectrum, you can see it's in some ways similar to some of the other spectra we looked at. And similarly, even though they use different atmospheric models, they also had difficulty in replicating the shape of the lithium line. But if we go back to the abundance plots that I showed before, this one, and compare with their plot, they show their new object 1644 in red, and compare that with some solar system bodies. Ignore the purple ones, which are upper limits. But if we take their data and put it on our plot, it appears up here. So it's sort of consistent with the other systems. But when we put it on this plot, things start to really, you see the difference. So it doesn't even appear on our plot. It's off to the side. And so this system really is not able to be explained by a crust composition. It has a potassium to sodium ratio that is much more similar to, say, the Earth or chondrites, or even the solar ratio. whereas LHS 2534 can't be explained by objects of this composition. It really needs something like crust. And again, if I put LHS 2534 on their diagram, it doesn't sit anywhere near their star, nor does it look like any of the solar system bodies that they compared against. And so I guess I'll wrap up with my conclusions there. But the main thing is we found white dwarfs with lithium and potassium, as have Kaiser et al. And there could be potentially two explanations of how you get lots of lithium in a white dwarf atmosphere. But potassium seems to be what you need to make that distinction. And yeah, modeling them is very difficult, and there's lots of work to do to do much better in the future. All right, so I'll stop there.
Thank you very much for your talk, Mark. Very interesting talk. For the people following the talk on YouTube, thank you for joining us. If you have any questions, please post them in the YouTube channel chat, and our speaker will answer them later. We'll be back next week with a seminar on transformations of galaxies in galaxy clusters.